Hi, this is Team 5. In this video, we are going to present our final project, Safe and Efficient Search on the replay buffer. Let me go over the introduction first. In our project, original paper that we try to replicate and improve is SORP, which is named after search on the replay buffer. The goal of this algorithm is to solve tasks that required reasoning over long horizon with limited feedback and high-dimensional observation. In order to achieve this goal, the author decomposed the task, which is reaching a distance goal state, into a sequence of easier tasks. They use planning algorithm to decompose the task and using learning algorithm, especially reinforcement learning algorithm, to solve a sequence of easier tasks. Here's the overview of a solve algorithm. Look at the picture A. The agent cannot reach the distance goal, but this algorithm constructs many replay buffer, and the graph is constructed from the replay buffer where the data is collected during the training procedure. And then, if the goal state is given, it searches the best path on the graph using the Dijkstra algorithm, which is one of the planning algorithm. And after getting the path from the current state to the goal state, the agent follows the path by using goal-conditioned RL policy. And our work to improve the SORP method is to make search safer pass more efficiently. To do so, we measure uncertainty of a distance estimate. With uncertainty information, we try to make a plan over edges whose distance estimates are more certain. We also prune edges in the graph where distance estimate model is less certain for efficient planning. And here are some related work for the measuring uncertainty. First way to measure uncertainty for neural network is use parametric Bayesian inference. We can regularize the weights by minimizing the variational free energy or the expected lower bound on the marginal likelihood. We can also use dropout training as an approximate Bayesian inference in deep Gaussian process. However, we cannot use additional regularization term since we need specially designed reward function. So in our approach, we utilize non-parametric way to estimate uncertainty. Specifically, we use non-parametric bootstrap from multiple neural network with random weighted initialization. Picture A shows the shared architecture for bootstrapping. And there are multi-heads with random initialized weights. And picture B shows a Gaussian process posterior for regression task. And picture C shows the result from bootstrapped network. Here you can see that it has high variance where the data point is given and small variance where the data point is given. It is very similar with the Gaussian posterior. We will explain how this method is used in detail in later slides.
So next is application and implementation. So we succeed to implement SORB algorithm as shown in this figure, referring to the authored code. And here we use distributional DDGP algorithm to train the agent. And this graph shown the replay buffer and the graph, and we succeed to construct this graph. And also we succeed to make the plan, waypoint plan on the constructed graph. And comparing the default policy and the SORB search policy has more accurate and more efficient result. And to implement, we tried as many as possible environment we had, as shown in this figure, to see how SORB algorithm works well or not. And As you see, without the SORB algorithm in this navigational environment, the agent cannot find well, but with the replay buffer graph, and we can draw, SORB can draw the waypoint as a yellow line, and finally we can see how the agent go. And with the similar environment as shown in this left and right, they can converge to the similar result. However, in specific environment, this does not work well. Even though the graph of the replay buffer works very well, some waypoints are invades the gray point, which agent cannot pass. And as a result, some agents converge to the corner, and also search policy has not come out with the not improvement rather than default policy. To solve this kind of problem, we are presenting new improvement algorithm called safe and efficient SORB.
Hi, this is the last presenter, Sung-Hoon Kim, and I will introduce our improved algorithm, which is safe and efficient SORB. First, we train multiple Q-value functions from the same replay buffer, each of which is randomly initialized and will be used as distance estimates between two states. And then we measure the variance of each distance estimates from these Q functions so that we can achieve the information of how confident of these trained models are. We ensemble these Q-value functions by taking average and construct a graph on the replay buffer. While making a graph, we prune the edges whose distance estimates have high variance. Finally, we use Dijkstra's algorithm to plan over the graph and runs the global goal condition policy to follow the waypoint from Dijkstra's algorithm. In our experiment, we trained three different Q-value functions, and this figure shows the illustration of constructed graph from each Q function. Although we use the same replay buffer and feed the same mini batch from this replay buffer in training, each graph is slightly different from each other because of random initialization. Here is a measured uncertainty from three different Q functions. We visualize it as a heat map where red edge has high variance and white edge has low variance. Please note that the variance is normalized to be ranged from 0 to 1. The left figure represents ensembled graph from multiple Q functions, and the right figure represents pruned graph based on the uncertainty, which is shown in the middle. On the pruned graph, if the goal state is given, it runs Dijkstra's algorithm to plan, as shown in this figure. And here's the qualitative result of our improved method, safe and efficient SORB. The first figure shows the trajectory without planning. The second figure shows the original SORB. And the last one shows the safe and efficient SORB. You can see that a wormhole problem happens because of inaccurate distance estimate in the original method. On the other hand, in our method, by removing edges of uncertain distance estimate, we can achieve safer path than the original method. So it successfully bypasses the wall and reaches the goal. In another scenario, the original method succeeds on reaching the goal. However, a wormhole problem happens again and it gives unsafe path. In our improved method, it gives much safer path. But sometimes our method fails to reach the goal. But the reason of failure is not due to the unsafe path. It fails because of the RL policy. For quantitatively analyze how safe our method is, we measure success rate. Safe and efficient SORB method reaches the goal with about 70% of success rate, which is almost 2 times higher than the original SORB method. We also measure the average time for planning to quantify how efficient our method is. Our method takes about 32.99 seconds for planning, while the original method takes 33.94 seconds. In conclusion, SORB algorithm enables the reason over long horizon, but by combining planning algorithm and learning algorithm. However, this algorithm is quite fragile when distance estimates from value functions are not accurate. So in our method, we measure the uncertainty of distance estimates and prune the edges with highly uncertain distance. As a result, planning algorithm gives much safer path and runs more efficiently. But we think that still there is a room for improvement. Although our method provides the way of measuring uncertainty and searching the path safely and efficiently, it is a post-op process, meaning that it doesn't really accelerate the learning procedure. So we believe that using a method that can explore based on uncertainty information would further improve our method.